Hello and welcome to today's lecture on biomathematics. We have been discussing calculus and we discussed differentiation and integration. Now, we will go to a new topic which is very closely related to what we discussed so far, very closely related to differentiation and integration, and it is called differential equations. So, today we will discuss differential equations. What are differential equations? That we will come to know as we go along. What exactly one means by differential equation, etc., will be clear as we go along. So, let us start with taking some example. So, what could be? So, let us take one of the example that is familiar to you when we discussed integration or when we discussed other calculus. So, let us take the simplest example, one of the simplest example of something polymerizing. So, one example is actin in biology. So, actin polymerizes or microtubules polymerize, or means there are umpteen number of polymers in biology and they all polymerize, and when they polymerize, as you know, their length increases. So, polymerization is nothing but adding monomers and the length increases. So, the question we have to ask is how exactly we will describe this mathematically, and the answer you will get is that this can be described by a differential equation. So, we use something called a differential equation to describe this phenomena of polymerization of a filament. So, that is what we will discuss to begin as a first example, and once we discuss, you will get an idea that what exactly differential equation means, and once you get that idea, we will discuss couple of examples today, one or two examples at least, and once you get this idea, we can go to the proper definition and so on and so forth. So, first I want to convey you the idea. So, let us take this example of actin polymerization. So, have a look at this slide. We want to study the polymerization of actin. So, actin is a filament as shown here, made of n monomers. So, there are many monomers 1, 2, 3, 4, 5, and then you can add monomer with some rate Kp. So, Kp is the rate of polymerization. So, with this rate, this monomers or the subunits are being added to this filament and the length of the filament increases. So, this is the phenomena. So, we want to describe a simple phenomena, and the question is how do we describe this using mathematics. So, as we see here, we have a polymer, and as the monomer keeps adding to this, the length of the polymer increases. So, let us look at the next slide. So, what happens is that the length changes with time. So, the quantity that changes with time is the length. So, we want to describe this mathematically. So, the question is how do we describe this using mathematics. So, this change in length that we see, how do we describe this mathematically? So, how do we describe the change in length mathematically is a question, and the answer to that is the following. So, have a look at this slide. So, we can say the mathematical description will have something like this, where dl by dt is equal to Kp. So, this is what written here. Now, what does this mean? dl by dt, as we saw, it means the change in length dl when the time changes by a amount del dt. So, the time how much is the length change when the time changes by an amount dt. So, when the time changes by dt, the length will change by an amount dl, and this happens with a rate Kp. So, that is what it means. So, the mathematical description of this phenomena of polymerization with a rate Kp can be mathematically it can be described by using this equation, which is dl by dt equal to Kp. That means, the change in length with time is Kp. So, now this such equations are called differential equations. as we see, the more the Kp, the more the change in length will be. You can see that. So, if because this Kp and dl are directly proportional, if you increase the Kp, the dl, the length and change length will increase even if you fix the dt constant. In other words, let us take dt as 1 second and Kp, let us assume Kp is 1. So, dt is 1, Kp is 1. So, let us write it down here. So, dl by dt is equal to Kp. This is the equation we said. So, let us make some sense out of this equation to begin with. So, let us take, so as we saw in the calculus when we studied differentiation, this actually means the change in length by change in time when time is very small. So, we can write when time is very small, we can write this equation in this particular way, dl by dt. So, when time is very small or delta t is very small, we can write this particular way. So, now let us say that delta t is very small, let us say a fraction of a second. So, let us say delta t is 0.1 second. So, then what does it mean? Delta L is Kp into 0.1. So, if Kp, the more the Kp, the more the delta L is. So, the Kp is 10. What does it mean? If Kp is 10, what does it mean? Delta L is 10 into 0.1 is equal to 1. So, the change in length will be 1 monomer per second. That's what it means. So, this differential equation has a meaning, and the phenomenon that we want to describe can be described by this particular equations. As such equations are called differential equation. As the name suggests, there is a differential here, there is a difference. You write a differential equation because there is a difference. The equation is written as a difference between 2 length and 2 time. So, this is what one typically means by differential equation. We will come little more carefully, we will define all this, but I hope you understand the concept, the idea. Now, given such equation, what does it immediately tell you? So, that is the next question one wants to ask. So, you have this equation which is dl by dt is equal to Kp, but what does that mean? What information does that give you? So, let us have a look at this. So, before that, we want to understand an important point that I want to describe here. The differential equation plays a very important role, very prominent role in all fields. Let it be physics, let it be engineering, economics, biology, the weather prediction, or whatever be the field you think of. Differential equations plays a prominent role. So, understanding differential equation is very important, whatever be the field you are interested in, including biology. So, we will spend some time carefully understanding differential equation, because it is one of the crucial, very important, prominent techniques used to understand or used to describe various phenomena, and understanding differential equation will help you in understanding how to describe various day to day phenomena that we see using mathematics. And at the beginning of this lecture, we said mathematics is like a language. So, this language is used to describe things in a precise manner, in a very quantitative, precise manner. So, as you know, once you understand this differential equation properly, you will get some idea, you will have a good idea how to describe various phenomena that we see around us in a very quantitative, precise manner, using a scientific language which is mathematics. So, you should keep this in mind when we study this differential equation. So, keeping this in mind, let us go and study and understand this particular differential equation that we have in hand. So, the differential equation that we have in hand is, as we said, is dl by dt is equal to Kp. So, when we see such an equation, what does it immediately come to your mind? Something we studied in the calculus, in the earlier differentiation in the previous lecture, or many of the previous lectures, we discussed something. So, that is something related to that of a straight line. So, let us just go back and see what we quickly see what we studied in the last lecture, something we saw in the last lecture, which is the following. So, when we discussed integral, we said it is like an antiderivative. So, integral as an antiderivative is something we discussed. So, for example, if we have a slope m, we can say slope is nothing but dy by dx. So, this is something that we discussed before. Slope is nothing but dy by dx. When we discussed differentiation, we said the slope is dy by dx. So, now this looks very much similar to what we described here. This dl by dt is equal to kp. This same as dy by dx is equal to m. So, there is like, you can see these are like similar equations. This is slope and dy by dx is slope. So, this looks very similar. So, this itself give you some hint what can we understand something about it. This has to do, this will have something to do with straight line. So, let us try and understand what is straight line here, but let us go back. So, in this slide, when we discussed dy by dx equal to m, m is the slope which is a constant. Here also kp is a constant, and we can integrate this equation. We said that we can integrate this equation and get y of x. So, we can integrate this dy by dx and get y of x. So, how did we do that? We did it in the following way in the last lecture. We said that in the previous lecture, we said that dy by dx is equal to m. So, and we took this dx this side and we said dy is equal to m dx, and we said we can integrate both sides now. So, we write integral dy is equal to integral m dx. So, which has nothing but integral dy is y and integral m dx is mx, and integration has a constant always, and that constant is c. So, this can be anything. So, this decides what is the value of y. So, this is an arbitrary constant as far as the integration is concerned. So, this is what we said the solution of dy by dx equal to m. So, keeping this idea in mind, keeping what we did in the previous classes, previous lectures in mind, we can try and go and understand this our polymerization problem. So, let us go this polymerization problem, which is we have dl by dt is equal to kp. So, we can write as we did in the previous case, dl is equal to kp dt, and you can integrate both sides. So, integral dl is equal to integral kp dt. This immediately tells you that L is kpt plus some constant, just like we said y is equal to mx plus c, where c is a constant, and we get the length as a function of time. So, what does it mean? For any given value of t, there is a value of L. If you change the t a bit, you will change the L. So, what does it mean? So, this is the solution of this differential equation that we discussed, and if the t is 1 second, it will give you what is length. If the t is 2 seconds, we will give you what is length. So, given a value of t, any number, you will get a value of L. So, if we can write down from this equation to the way of going from dl by dt to L is equal to kpt plus c, we call the solution of the differential equation. So, in this slide, we have solved the differential equation and we wrote down the solution. The solution will give you how does the length change, the length changes as a function of time. So, that is the solution of the differential equation. So, we have solved the differential equation and got the length for any value of t. So, let us look a little more carefully and let us try and understand this. So, let us look at this slide. So, what we have got length as a function of time. So, this bracket t means length depends on the value of time. So, length is a function of time, that is what it means. We discussed what a function is in the early classes. So, length as a function of time is given by k p t plus c. Now, how do we get this c? So, let us take in this case t equal to 0 in the above equation, and what do we get? If we take t equal to 0, we get L at t equal to 0. When t equal to 0, the length is nothing but c. So, c, it turns out that c is nothing but the length at t equal to 0, or you can say initial length. When we start the experiment or when we start the discussion, what was the length? So, if you imagine, if you are doing an experiment, you have actin with a length to, or polymer with a length to begin with, you immediately add things and let it start polymerizing. The length that when the polymerization starts, whatever be the length, that is, you can call it as initial length. So, if you the c, it turns out that c is nothing but the initial length, as you can see here. C is nothing but length at t equal to 0. So, the length, initial length of the actin filament. So, known this, we can write down the following. So, what did we get now? We got L of t is kpt plus length at t equal to 0. Let me call it L0. So, this is length at t equal to 0. If you know the length at t equal to 0 and if you know the kp, you can get length for every time. So, if you, so let us say L0 is 4 monomer. So, L0, so let us say to begin with, we have 4 monomers. So, to begin with, we have a polymer which has 4 monomers. Now, you add monomers with a rate Kp, and let us call this Kp as 1 per second. So, in every second, 1 monomer will be added. That is what Kp equal to 1 per second means. The rate of addition in every monomer, every second, 1 monomer will be added and the it will polymerize. So, then the length at any time t is given by Kp is 1. So, 1 into t plus L0 is 4. So, now this is the solution, that is, for if it is t is 10, that is after 10 seconds, you will have 10 into 1 plus 4, 14. So, let us say, let us think of a column here, right. So, we can think of a tab. So, we can have time here and the length here. So, when t is equal to 1 second, 1 into 1 is 1, 1 plus 4 is 5, the length is 5. When t is 2, that is t is equal to 2 seconds, t into 2 into 1, 2 plus 4, 6. When t is 3 seconds, 3 into 1 plus 4, 7. So, L becomes 7, 3 into 1 plus 4, 7. So, this is similarly, if it goes and let it be 10, then t is 10, 10 into 1 plus 4, 14. So, for any value of t, there will be a value of L. What does that mean? That means that we can plot this as a function of time. So, let us plot here. So, let us plot length as a function of time. So, this is the length of the polymer as a function of time, and t equal to 0, we had 4 monomers. So, this is t equal to 0, we had 4 monomers. So, this is 4, and as the time increased, it increased like a straight line. So, we had L is Kp into t plus 4. This was our equation. This is the equation that we have plotted, where Kp is the slope of this, Kp is the slope of this straight line. So, just like the equation looked similar to that of y is equal to m, dy by dx equal to m, which immediately gives you y is equal to mx plus c, which is equation of a straight line. This is just like that. this differential equations will give, the equation will give you dy by dx is equal to Kp will give you L is dl by dt is equal to Kp will give you L is equal to Kp t plus C, which is nothing but a straight line. If you plot the length as a function of time, it is a linear line having the slope Kp. So, the differential equation dl by dt is equal to Kp will give you a straight line, and physically, biologically it means that if you have a constant polymer Kp is a constant, then the length will increase in a linear manner with a constant, like it will increase, it will increase as a straight line, as we see in this plot, it will increase like this. So, this is like a linear function as we see here. Okay. So, this is what you see here is a linear function where the length increases with time as a straight line. Okay. So, we understand this now, we understand polymerization, and we understand how do we describe polymerization using a mathematical description. But now, let us ask, if we want to describe, let us a depolymerization, how does this change? Like, so we had this equation, differential equation, will it change if we want to describe depolymerization? What change will it have? So, let us think and understand in the case of depolymerization. Have a look at this slide. What you have is, you have a polymer, as we said, instead of polymerizing, it is always depolymerizing. So, Kd is the rate of depolymerization. So, when the depolymerization is the rate d, the length of the polymer decreases. So, this is something which we all know, that when it is depolymerizing, what will happen? The length decreases with time. So, this is what happens. If you have a polymer, just depolymerizing. So, the length decreases one by one. So, it just shortens, the polymer shortens. So, this is what physically happens. So, now in the previous case it was length increase, in this case it is length decrease. So, that is the difference. If you polymerize, the length increases, if you depolymerize, the length decreases. But in both the cases the length changes. So, there is change in length in both the case, there is a number rate with which it increases or decreases, but in this case it is decrease. So, we have to somehow put in this difference, increase and decrease. So, they are opposite things. So, how do we put in something mathematically, increase and decrease? So, we will, as you know, like increase, we always use like positive is increase and negative is decrease. You add 2 plus 3, addition is increase in the value, and subtraction 2 minus 3 is decreasing the value. So, the minus or the negative implies will give you this idea of decrease. So, we know this from the numbers, and we will use exactly the same idea here. So, whatever we had previous plus a negative. So, let us see what do we get. So, have a look at this slide. So, we will write dl by dt, which says, so this left side only says that the length changes with time. dl by dt means dl, the length and change in length with dt. When the time changes by an amount dt, the length changes by an amount dt, but this change is decrease here. So, we have to say specifically the change is decrease. So, when it is decreasing, it is a minus sign. So, look at the slide here, it is a minus sign here. So, dl by dt is minus Kd, where Kd is the rate of depolymerization. So, this is the crucial difference, this minus sign, then the meaning changes completely. Now, we are describing a phenomena where the change in length is decreasing. Previously, it was a plus here, we had dl by dt is equal to plus Kp. So, then it was an increase, here it is a decrease. So, this is the crucial difference. So, when we want to describe something is increasing, we will use plus. something is decreasing, we will use minus. This is a standard thing in mathematics, we will make use of that, and then let us see what does that give, how does that change our answer. So, let us look at the slide, next slide. So, we had this equation, we have this equation dl by dt is equal to minus kd. So, look at this solution here, what is written in this slide. So, as you see here, what do you see? dl can be written as minus k dt. Now, we can integrate on both sides. So, you can integrate here and integrate here, and you get integral dl is equal to minus integral k dt. So, if since you have this minus sign here, the integral of dl is L, but integral of k dt, since k d is a constant, it is like just k dt plus a c. So, since k d is a constant, you can take it outside and then you can write it as k dt plus a constant. So, we get length as a function of time here again, but there is a minus sign here. So, what does that mean? We will see what does that mean. So, what does that mean is that, so let us have a look at what does that mean here. So, let us look at this here. So, we have L as a function of time, which is minus k dt plus c. So, just like we had in the previous case, when t is equal to 0, what do we have? When t is equal to 0, we have L equal to L of 0 is equal to minus k d into 0 plus c. So, this is 0. So, L at 0 is equal to c. So, we get that c is again the initial length. So, we can write L at t, we can substitute this back to the c. So, we can write c as L 0. So, let me call L of 0 as L 0. I just write L of 0 as L 0 for convenience. So, L of t is nothing but minus k d into t plus L 0. In other words, it is L 0 minus k dt. So, previously it was L 0, here it is plus, now it became minus. So, whatever be the initial length, from that it decreases as the time goes. So, this is again a straight line with a negative slope. So, this is like y is equal to c minus mx. So, m has a minus sign here. So, this will look like a decreasing function. So, let us see how does this plot, when we plot it, what do we get. So, let us look at how do we plot this. So, have a look at here. So, we can plot length versus time again here, length of the polymer versus time. So, at t equal to 0, we have some initial length which is L 0. So, let me mark this initial length as L 0. So, this is our L 0, and as the time goes, it decreases. So, it decreases like a straight line. So, L is equal to minus k dt plus a constant. So, in the previous case, we had an increasing a function that was increasing, here we have something that is decreasing. Okay, so, this is the way differential equations work. So, we saw two differential equations, but essentially the part of the same idea. One was polymerization, the other one was depolymerization. Now, given this two you understand, let us go to a slightly different case, little more complex case, and let us see for that phenomena how do we write down the differential equation. So, what is that? Again we will use another example that is we are very familiar with, that is the example of like cell division or the bacteria. We will take for example here the case of bacterial cell division. So, the number of bacteria, they divide and divide and divide, and the number increases. So, how do we describe this phenomena? using a mathematical description. Again we will come and we will have to use differential equations, and that is how we will try and understand about. So, let us look at the next slide. So, we want to say bacterial growth. So, the example is, we could say example is E. coli. So, when you have E. coli, you start with some, let us say one cell, it divides into 2 in about 20 minutes. So, that is a typical time with which bacteria divides, and it again divides into 2, each of them divides into 2. So, again 4, they again divide into each of them again to 2. So, 8 and so on and so forth. So, they divide 2, 4, 6, 8, 16, 32. So, then it just keeps increasing. Each of them can divide. So, if there are 3 of them, all 3 can divide and become 6. And if there are 6 of them, all 6 can divide and become 12. And if there are 12 of them, all the 12 can divide and become 24. So, in this case there are 2 points to note. So, let us have a look at what are the 2 points to note. So, one is the number of bacteria increases with time. So, the number increases, there is no question about it. As the time goes, the number increases, and the more the bacteria, the more the increase. If there are, that is what just now we were discussing, if there are like 10 bacteria, all the 10 can divide. So, 10 will become 20. If there are only 2 of them, 2 can become 4. So, they increase only by 2. So, let us try and understand this a bit more. What do we mean by the more the number, the more the increases. So, let us look at here. If there are 10 bacteria, they divide and go to 20. So, the difference in numbers. So, then at begin with the 10 and then became 20. So, the difference in number is 20 minus 10 is 10. So, the increase or the change in number is 10. If there are only like 2 bacteria, they will go to 4. So, the change is just 4 minus 2, which is only 2. If there are 100 of them, they will go to 200. So, they increase by 100. So, the delta n will be 100. So, the more the number, the more the increases. So, what does that, how do we say this mathematically? So, here we had 100, the delta n was 100, here we had 2, the delta n was 2, here it was delta n was 10 and the delta n was 10. So, 2 has delta n 2, 10 has delta n 10, 100 has delta n 100. So, the delta n what we have here is proportional to the n. So, what does this, how do we say this mathematically? We can say the delta n is proportional to the n itself, because we said that when we had n and delta n, we had previously 2 had delta n 2, 10 had delta n 10, 100 has delta n 100. So, the delta n is proportional to n. In other words, the change in number when the time changes increases with time. In 20 minutes, in a given time delta t, they increases proportional to n. If there are more of them, they will increase more. So, this proportionality constant can be anything that is proportional in mathematics, can be changed to equal to by adding a constant k. So, you can write delta n by delta t is k n. Now, you have to say this is a plus sign here because this is increase. As we said, there are 2 points to note. So, look at this slide. The 2 points to note is that first it increases with time. The second point is that the more the bacteria, the more the increase is. So, combining these 2 points, we get the following equation. So, let us look at the next slide, the equation, the mathematical description is the following. The dn by dt is plus kn. The plus represents the increase, not the decrease, it is increasing, and the fact that it is kn is proportional to n implies this phenomena that we see, that the more the n, the more division will happen. So, the more there are more numbers to divide, so the increase will be more. So, we combine these two ideas into one line and we got this equation dn by dt, the change in number when the time changes, thus dn by dt is equal to plus kn. So, we have a new mathematical equation mu. So, this is another kind of differential equation. Previously, we had only some equation, there is no n, something like dn by dt equal to k. So, like we had dl by dt is equal to k. So, then we knew how to solve it. Now, we have dn by dt is equal to k times n. So, how do we solve it? So, let us look at the next slide. We will try and do this in a similar way that we did. So, let us look at the next slide. So, we have dn by dt is equal to kn. So, that is this equation that we have. We can rewrite this as dn by n. So, we can take this n below and dt the other way. So, dn by n is equal to k dt. So, that is what this says, dn by dt is k dt. Now, you can integrate both ways. So, dn by n is integral k dt. So, that is what this says. So, dn by n is integral k dt. Now, what is the integral dn by n? So, as we studied before, integral d by n by n is log n, or we also studied the derivative of log n is 1 over n. So, integral of dn by n is log n, and integral of k dt, since k is a constant, integral of k dt is k t plus you have a constant of integration k t plus c. Now, this log is a natural log, it is log to the base e or ln. So, we can anything log y is equal to x, you can write y is equal to e power x exponential, like we studied this. So, let me say we studied that log to the base e y is x, y is e power x. In other words, ln y is x, y is e power x. So, this is something that we studied before. So, keeping this in mind, we end up this answer, that is log n. If you have log n is equal to k t plus c, as we have it here, we can say n is equal to e power k t plus c. Now, what is c? Let us have a look at as before. So, what do we have? We have n, the number of bacteria, as a function of time. So, for a given value of t, given k and c, you have n. Now, as before, when t equal to 0, we get n of t equal to 0, that is n 0 is equal to e exponential c. Whether this k t becomes 0, k into t becomes t is 0. So, k t is 0, this term is 0. So, e power c is equal to n 0. So, we can write this equation, the substituting this e power c back. So, you know trick in mathematics that, so what do we have here? E power k t plus c is equal to n of t, that is what we had, and e power k t plus c can be written as e power k t into e power c. In mathematics, e power a into e power b is e power a plus b. So, known this identity, you can write e power k t plus c as e power k t into e power c. So, that is what we did, and this e power c is nothing but n 0. So, that is what we did here. So, we know that e power c is n 0. So, n of t is n 0 e power k t. So, we can write it this way. So, what does this mean now? So, what does this n of t is equal to n 0 e power k t means? How does this graph look like? If we plot this, how does it look like? So, let us plot this n versus t. For every t value there is an n, and our equation is n is n0 e power kt. So, when t equal to 0, n equal to n0. So, when t equal to 0, this is t equal to 0, n has some particular value, let me call this n0. So, this is 0 and the t increases. Now, this is an e power is an exponential function, and we have seen how do we plot exponential functions. So, this is they increase like very fast. The straight line will be something like this, but if a straight line, it looks something like this, but this increases very fast, much faster than straight line. So, this is exponential increase. So, this is n is equal to n0 e power kt, exponentially increases. How fast they increase, that will depend on the value of k. We will discuss how does the value of k depends on many other things, etc. That is something we can discuss, but at this moment, for you to understand the differential equation, it is sufficient to say that given a value of k, you can write down such a solution, and that will give you this exponential growth that we study in any growth curve, right. When we have any growth curve, we have this exponential growth. So, let us for the moment go back to the slide, the previous slide. We had this log n is equal to kt plus e. So, let us see what we get if we plot this equation. This is also we started from dn by dt is equal to kn, and we got log n is equal to kt plus e. So, when we have this log n equal to kt plus e, what do we get? So, let us plot log n here and t here, and if you plot log n is equal to kt plus e, which is actually the solution of this equation which we wrote for the bacterial growth, this part we will get, this is like y is equal to m into x plus c. So, you know that this will look like a straight line. So, this is what typically you call the log phase. In biology, we call log phase, right. So, the growth, there is a log phase of growth. So, we have such an equation, there is a growth which we draw, most of the time we draw straight line. The way we draw, the reason that we are drawing straight line is precisely this, that in the x, the y axis, we are plotting the log n, not n. So, if we plot log n in the y axis and t, this part will look like a straight line. So, this is we can call the log phase of bacterial growth. This is what we described, or log phase or exponential phase. So, this is exponential growth. So, exponential growth sometime you can see it as a straight line people draw, that is because you plot log n versus t. If you plot on the other hand n versus t, it will look like an exponential graph. So, it depends on what you draw. People sometimes call it exponential phase, sometimes people call it log phase. So, essentially it is the same thing. So, this equation that we said dn by dt is equal to kn, this differential equation that we described describes the log phase or the exponential phase of growth. So, again we used a mathematical description, an equation to tell you something about this phenomena, and it precisely tell you after 10 minutes, if you tell me at t equal to 0, how many cells you start with and the rate of cell division, we know that we can say that this will tell you, this equation will tell you how many of them are there as a function of time. Okay. So, we discussed polymerization, we discussed cell division or growth. Any growth, this can be applied to any growth. As we can see, it is very general. It can be any number, it can be bacteria, it can be something else. So, that is why I use k. K is some general rate of growth. It could be even like rate of like number of population, right. The population can grow exponentially. If we had nobody was dying, right, it had only growth, then things would exponentially grow. We didn't take any death into account, we had only the growth, so we exponentially grew. So, okay, now let us think of how do we take the death into account, or in the case of cell it is like apoptosis, that is cell death. So, how do we take the cell death into account? How do we describe that mathematically? We had polymerization, depolymerization. The difference was that polymerization things increased, the length increased, in depolymerization length decreased. In the case again, the number increases when it is cell growth, in apoptosis it is the number decreases, or cell death the number of cells, live cells decreases. So, how do we describe that? Just like we did, a minus sign will do. Like we had this minus sign idea for this. So, let us look at this here. When we have apoptosis, we can describe that by writing dN by dt is equal to minus kn. And as we just saw, we can solve this again the way we did, and we will get a solution. N of t is n0 e power minus kt. So, the solution has a minus sign here, e power minus kt. We had previously n0 e power plus kt. So, now it is a minus kt here. So, now how do we draw this if we want to draw? So, let us draw this n0 e power minus kt. So, let us look at here. So, we have n and t, and at t equal to 0 we have n0, that is this, and what we want to say is that n0 n is equal to n0 e power minus kt, exponential minus kt, and that will look something like this. As the time goes, the number increases exponentially. If it was straight line, we would have got something like straight line like this, but here is exponentially decreasing. So, this will describe this equation n equal to n0, and so this is a solution of dN by dt is equal to minus k times n. So, this is the case that we discussed. So, let us see what we have. So, we have what we studied is like two kinds of equations, and such equations are called ordinary differential equations. Now, why this ordinary? We will discuss this, because when we discuss some other type of differential equation, we will understand the difference, and we will say what is ordinary differential equation and what is some other differential equation. So, such differential equations, two examples, dl by dt is equal to minus kd or dl by dt is equal to plus kd, this describing the rate of change of length, the length increase or length decrease depending on the minus or plus sign, plus or minus sign, is described this first equation. The number increase is described by this equation. So, the first equation precisely decreases the decrease in length of anything, a polymer. If L is a length, dl by dt is minus kd is the rate of depolymerization kd, then this will describe the depolymerization of any polymer, for example, actin. This dN by dt is equal to kn will describe the number increase of anything that is growing. So, bacterial growth or in yeast cell growth, the log phase or the growth phase or the exponential phase of it will be described by this equation. So, basically what we said, we found that to solve this equation, as we see here in the slide again, to solve this we need to have one constant, the C thing, and that we call initial condition, because since it is involving time, this is always at time equal to 0. If we know this solution. So, what we call it is initial condition. At the beginning of the experiment, how many numbers are there or what is the length, by knowing that we can solve this. So, let us summarize what we saw. So, to summarize, the biological phenomena can be described mathematically using differential equations, and for examples we describe polymerization and depolymerization of actin, bacterial growth and cell apoptosis. and knowing one constant, which is the initial condition in this case, we will describe, we can solve this equation and get length or number as a function of time. So, this is what we learn in this class. In the next class, we will describe more differential equations and try and learn how do we solve them, and thereby how do we describe various mathematical phenomena. Thank you very much.